Hi everyone, I am Tamícera Silva, a doctorate student from University da Paraíba and Université do Litoral Coté-do-Pal, and it's a pleasure to present this work for you today. Calcium aluminate-based fibers produced by solution blow spinning as a potential catalyst for steam methane reforming. CO2 emissions caused by the entire energy chain can reach 750 gigatons in the next 5 decades. The average global temperature, if anything change, can increase by 4 degrees in the same period. The COVID-19 pandemic reduced the global energy demand by 3.8%. And this was caused because of the less necessity of mobility and economic activities was paused. So the CO2 emissions dropped 8% because we use less fossil fuels. So, how to produce energy in a cleaner way? The hydrogen is a good alternative, but to produce hydrogen is necessary use this technique, steam methane reforming. Steam methane reforming is a technique which is possible to break the bounds between hydrogen and carbon in the presence of water and produce carbon monoxide and hydrogen. And every time is followed by the water gas shift reaction, which takes the carbon monoxide with water and produce carbon dioxide and hydrogen. Some characteristics of steam methane reforming is the necessity of high temperatures, low pressures, the deactivation of catalysts by carbon deposition, and particle sintering, and high emissions of CO2. But if we try to reduce the emissions of CO2, it's necessary to do something. So to do that is capture the CO2. And to capture the CO2, we use the technique called sorption enhancing steam methane reforming, which is the same steam methane reforming but with a step more, the CO2 capture. This technique has like a characteristic increase the CH4, the methane conversion rate, production of high purity hydrogen, use of less temperature, so a lower temperature, operating temperature, use of sorbent materials which is capable to recycle after multiple cycles of carbonization and calcination, and is a technique which improves the energy efficiency and reduce the cost for hydrogen production. The purpose of this study is to produce ceramic fibers by solution blow spinning with a calcium aluminate composition to be used like a bifunctional catalyst to sorption enhancing steam methane reforming process. In first step is produce the supports, synthesize and characterization of supports, catalytic tests, and characterization of the test to produce more samples to like a bifunctional catalyst. For the experimental part, we choose like material, like composition. The Mayanita phase is a calcium aluminate phase consistent with 12 parts of calcium oxide and 7 parts of alumina. After, to obtain this composition, we use the method solid-state reaction and solution blow spinning. And the conditions of operation to produce the supports was mixing the calcium carbonate from seashells waste with aluminum for 10 hours and calcinate, and after a process of calcination. The solution blow spinning is a technique which used only a pressure gas with a solution in an airbrush conventional commercial to obtain fibers and nanofibers in a collector. To obtain these fibers was used the PVP solution with nitrates, calcium and aluminum nitrates in the stoichiometric quantities, an airbrush, and after a step for calcinate these fibers in a ceramic fibers. After the preparation, after the production of supports, they were characterization by BAT, XID, SEN, and TG. The wet impregnation was used to produce the catalysts. So we calculate 15% of nickel in the end of the catalyst. And this catalyst was reduction in the step for the pre-step for catalytic test was reduction in hydrogen atmosphere for 1 hour at 800 degrees. To the catalytic test, the temperature program was 500 until 800 with a gap of 50 degrees between each temperature. And we use two proportions of two ratios of methane and steam, 1:1 and 1:3. The partners, we can see the supports prepared by different routes, the solid state reaction and solution blow spinning. They both show the presence of magnetite phase and the calcium aluminate phase, which is near to the magnetite phase in the diagram calcium aluminate phase. The physical properties of supports show the fibers produced by solution blow spinning has a specific surface area bigger than the powders produced by solid state reaction. And the pore specific volume is bigger too. In the SEM image, we can see the fibers before calcination and after calcination. We see the density of quantity of fibers is less when we do the process of calcination, because the PVP lost almost 90% of your mass during the process. And here we can see the porous, the fibers with a big porosity, which can be a good property for catalysts for sorption enhancing steam methane reforming. After the process of impregnation, we tested the specific surface area, and both samples increase your specific surface area, probably because the process of hydration of calcium aluminate. When the calcium aluminate is hydrated, it's easier to achieve the magnetite phase, like it's possible to see in this XID pattern. And we have more magnetite phase for solid state reaction than for the fibers produced by solution blow spinning. In both cases, we have the presence of nickel oxide and calcium oxide too. After the process of reduction, we have the nickel in metallic form. The methane conversion of catalysts with composition with 15% of nickel and magnetite, we have the same behavior. At 650, we have the more than 80% of conversion to the samples prepared by solid-state reaction, independently of the ratio of methane steam. And in every temperature, the nanofibers prove not to be so distant of the results of the powders produced by solid-state reaction. So these results shows it's possible to improve the nanofibers to achieve a quantity, at least at the same quantity of conversion, but if you improve the parameters and the morphology of nanofibers, we can achieve more than CH4 conversion than the powders produced by solid-state reaction. Conclusions. In this work, was possible to obtain supports produced by solution blow spinning with a magnetic crystalline phase, and this technique proved to be capable of producing porous ceramic fibers capable of converting methane to a similar level as the sample prepared by solid-state reaction at temperatures above 650 degrees. The potential of the fibers can be improved by adjusting the preparation conditions. So the next steps of the work consist of adjustment in the fiber production and preparation with another composition to see the efficient to use like a sorption enhancing steam methane reforming process. Thank you for watching me, and if you need more information, this is my contact. Bye.